Okay, so welcome to the very last session of the conference. There will be 3 talks in this session. The first talk will be given by Eunjeong Kim, and it will be about MemSpec, memory-aware runtime for adaptive draft scheduling in speculative decoding on edge devices. Please.
Oh. Hello everyone, I'm Eunjeong Kim from the Computer Systems and AI Lab at Kyungpook National University. Today, I'd like to present our paper, MemSpec, Memory-Aware Runtime for Adaptive Draft Scheduling in Speculative Decoding on Edge Devices. Let me start with some backgrounds. Most modern large language models rely on autoregressive decoding, where tokens are generated one at a time. Since each token depends on the previous one, generating n tokens require n sequential target model execution. This sequential nature limits parallelism and becomes a major bottleneck for LLM inference. One of the most promising approaches to address this bottleneck is speculative decoding. The idea is that a lightweight draft model first proposes multiple candidate tokens, and the target model verifies them in a single execution. As a result, multiple tokens can be generated per target model execution, leading to significantly higher throughput. However, the effectiveness of speculative decoding heavily depends on the choice of draft model. Domain-specialized drafts, such as a model fine-tunes for code or math, performs well within their target domains, but often degrades on out-of-domain inputs. To quantify the impact of draft selection, we evaluated performance on Jeon or Nano. First, we compared 2 approaches, general static and oracle static. General static used a single general purpose draft model for every prompt. In contrast, oracle static evaluates all candidate drafts offline and selects the best one for each prompt. Oracle static improves token acceptance by 40.3% on average. This shows that choosing the light draft model can significantly improve speculative decoding performance. More interestingly, the optimal drafts can change during generation. Oracle Dynamic, which adapts draft selection during generation, improves token acceptance by an additional 25.7% over Oracle static on average. This suggests that static selection is not sufficient. To adapt draft selection during generation, existing approaches rely on online exploration, such as multi-armed banding methods. Since the best model is not known in advance, they try different models and observe their performance. Over time, they learn which drafts works best. However, these approaches cause problems on edge devices. On edge devices, GPU memory is limited, so only a subset of drafts model can reside in GPU memory. When exploration selects a non-resident draft, it must be loaded from a slower memory. On the Jeon or Nano, loading a non-resident draft takes 2.7 times longer than a single draft and verify iteration. As a result, frequent draft switching can significantly slow down generation. We evaluated MAV-based adaptive speculative decoding methods. As expected, They improve token acceptance by identifying better draft selection. However, as shown on the slides, a large fraction of execution time is spent on draft loading or fallback execution using a suboptimal draft model. As a result, the gains from better draft selection are largely offset. In other words, better draft selection does not necessarily lead to throughput on the edge devices. To summarize, dynamic draft switching can improve performance. However, on edge devices, switching costs are too high to fully realize those gains. The key problem is that the best draft may not be immediately executable if it is not resident in GPU memory. Existing methods focus on finding the best draft, but ignore whether that draft is actually available. This leads to our key insights. On edge devices, we must jointly optimize draft selection and draft availability. To address this challenge, we designed MemSpec around two principles. The first is proactive draft residency management. Rather than reacting after the draft is needed, MemSpec predicts promising drafts early and keeps them resident in best memory. This aligns draft residency with future demands. The second is decoupling draft selection from execution. Rather than blocking on non-resident drafts, MemSpec continues decoding with the best currently resident drafts while preparing better candidates in the background. This allows decoding to make progress without waiting for model loading. MemSpec implements these two principles through three components: prediction engine, draft model cache manager, and runtime controller. I'll briefly explain each component. First, the prediction engine. Instead of exploring multiple draft models online, MemSpec predicts the best draft model for the current context using input prompts and recently generated tokens. We implement these predictors using a lightweight BERT-based model. Second, the draft model cache manager. Based on the predictor's ranking, it keeps high-priority drafts in best memory and asynchronously pre-patches promising candidates. This helps ensure that the right drafts are available when they are needed. Finally, the runtime controller. It always learns the best available drafts while preparing better candidates in the background. As a result, decoding never has to wait for model loading. Let me walk through how MemSpec works at runtime. We start by learning speculative decoding with the best available drafts already resident in best memory. Meanwhile, the prediction engine analyzes the current prompts and recently generated tokens and ranks the candidate drafts. In this example, D2, D1, and D5 are the top three. Based on this ranking, the cache manager then evicts lower priority drafts and asynchronously pre-patches the top-ranked ones. Decoding continues throughout this process. Once pre-patching completes, the runtime controller switches to the better drafts at the next scheduling points. And this process repeats throughout generation. Now, let's move on the evaluation. For all experiments, we used an NVIDIA Jetson Orin Nano. For models, we used Llama 2 and Qwen 2.5 with 7 billion target models quantized to int4 using GPT-Q, and draft model around 0.5 billion parameters. We use prompts from diverse dataset spanning 5 domains: general, code, math, law, and medical. We compare 5 draft selection strategies. First, general static use a single general purpose draft for all prompts. Second, Oracle static evaluates all candidate drafts offline and selects the best one for each prompt. Third, MAB async is a state-of-the-art exploration-based approach. And fourth, Oracle Dynamic assumes perfect knowledge of the optimal draft at every scheduling point and serves as upper bound. Finally, we compare MemSpec against all of these baselines. This graph shows normalized throughput, where all results are normalized to general static. MemSpec improves throughput by 40.7% over MAB async on average. The key reason is that MemSpec jointly optimized draft selection and draft residency. It not only selects better drafts, but also ensures they are resident when they are needed. Compared to Oracle Dynamic, MemSpec achieves 95 to 97% of its performance. This means near Oracle performance without expensive offline evaluation. To understand where the performance gaps come from, we break down execution time into 3 components: desired execution using the prepared drafts, fallback execution using a non-prepared draft, and prediction overhead from running the predictor. This graph shows execution time normalized to MAB async. MAB async spends nearly half of its execution time on fallback execution. However, MemSpec reduced this to below 5% while increasing the fraction of desired execution. Prediction overhead remains below 3.9%. This confirms our key insights. Better draft availability leads to fewer fallbacks and higher throughput. Finally, we analyzed the contribution of each component. Prediction only used the predictor without proactive prepatching. Prediction alone improves token acceptance, but a large portion of execution time is still spent on fallback execution. Once residency management is added, fallback execution drops below 3%. This result shows that prediction alone is not enough. The key is ensuring that the predicted drafts are actually resident when they are needed. To summarize, the real bottleneck in adaptive speculative decoding on edge devices is not just selecting the right drafts, but ensuring that it is ready for execution when needed. MemSpec addresses both through prediction-guided residency management. As a result, it improves throughput by 40.7% over MAB async and achieves 95 to 97% of Oracle Dynamic performance. The key takeaway is that timely draft availability is the key to realizing adaptive speculative decoding on edge devices. Thank you for your attention. I'd be happy to take any questions.
Are there any questions?
Yeah, maybe I'll ask something. Thanks for the presentation. So I was wondering, like, you evaluated this on this Llama and the other model.
Yep.
Are these traditional edge workloads? And maybe you can comment to, like, if then you execute even smaller models, how this will change? Because I guess this overhead of the availability depends largely on the size of the model, or not?
Size of draft model, target models? Or
Yeah, so you evaluated on Llama and another one, right?
yep.
And I was wondering if those results will change if
Yep.
you use smaller. For edge devices.
Yep. Let me think for a moment.
Okay, so if there's no more questions, so let's say
In draft model, for QM, 0.5 billion model is the smallest available models, and we used similarly sized drafts for Llama. And target model
You can take that offline.
thank you.